Okay, so we are very happy to have Shahin, who is going to give his talk on a recent work on low dimensional gravity, I think, and and we are very happy that he's finally giving this talk to us, and we have many people joining us also from Iran. Welcome to all of them, and also to everyone. So over to you, Shahin.
Okay. Thank you, Ayan, for the invitation and for giving me the opportunity to talk here. This is actually a work that a series of works that we have been doing in the last 3-4 years in some different collaborations. I've put the name of my collaborators here, but in the maybe last part of my talk, I'll focus more on lower dimensional, in particular 3-dimensional gravity, to just show how the ideas, general ideas that I present here could be worked through in specific theories of gravity. So please let me know if you have any questions as we go along. Feel free to ask questions. So this is the outline of my talk. I'll basically motivate the problem that I'm going to study here and tell you about through the questions regarding black holes, and in particular black hole microstate problem. And basically we'll try to see if studying more closely the physics near the null boundaries, which is basically a model for black hole horizon, can give us a handle on the microstate problem. In particular, I'll basically focus on what I will call boundary symmetries. Maybe you have all heard about the asymptotic symmetries, but the same process, the same ideas could be applied to any surface in the space-time, including in particular null surfaces. And I'll basically work out null boundary symmetries in the 3-dimensional example, and basically discuss their algebra and many other features of this null boundary symmetries. And basically I'll end by summarizing up the results and basically discussing how it could be related to the black hole microstate problem. Okay, so let me just very briefly review what we know about black holes. Black holes classically are solutions to Einstein gravity or any generally covariant theory of gravity. And there are many different black hole solutions within diverse dimensions. Regardless of the details, classically, any black hole is specified by a horizon, and horizon is typically a null surface which divides the space-time into two causally disconnected regions, which we usually call in or outside regions of the black hole. And within the standard GR, or in general gravity theories, we know that horizons and black holes can dynamically form through the gravitational collapse process. Again, regarding horizons, we know that for stationary black holes, horizons are smooth, non-singular null surfaces. And horizons, as I just briefly mentioned, could be viewed as a boundary of outgoing causal curves in the outside region of the spacetime. So if you're in the outside region of the spacetime and you never pass through the horizon, then so there's a big class of observers with this property, and horizon for all of them, all of this class of observers is like a boundary of space-time. So an observer who is always outside the horizon basically finds the horizon as its boundary, the causal boundary of the space-time region for this class of observers. And again, if we want to give some more abstract definition of horizons, in general, horizons could be which are could be defined as null surfaces, which could be observer dependent, like the Rindler horizon, which is basically the horizon of an accelerated observer, or it could be a global property of the space-time. That's when we are dealing with a black hole with an event horizon. So this was basically about black holes at classical level. Semi-classically, as we all know, black holes admit a thermodynamical description, meaning that they Hawking radiate, they have entropy, and they evolve as governed by the laws of thermodynamics. But black hole thermodynamic properties like chemical potentials and mass and other charges are often attributed to the horizon. And among these thermodynamical quantities, entropy is very special in the sense that it's dimensionless and is observer independent. Actually, all the other black hole thermodynamic properties, except for the entropy, are observer dependent. And so this is why entropy is so particular. This means that all the observers, different observers that you can have in your black hole geometry, must measure the same value for the entropy, while the same different observers may not agree on the values of the charges and or the chemical potentials and in particular the temperature. We have this celebrated Wald's formula and Wald's derivation for the first law of black hole mechanics that basically tells us how to compute the entropy of a black hole for any given black hole solution for any given diffeomorphism invariant theory. According to Wald's derivation and Wald's entropy formula, the entropy only involves the black hole solution and the gravitational part of the action. By gravitational part of the action, I mean the part of the action, the gravity theory action, which involves curvature. So, as you know, in general, in gravity theories, the action has two parts. The gravitational part, which involves curvature, and the non-gravitational part, which is usually called the matter part. So Wald's derivation tells us that the entropy only receives contributions from the gravitational part of the action. And chemical potentials in this thermodynamic description, like temperature and horizon angular velocity or horizon electric potential, depend only on the metric or on the solution and not on the theory, whereas the other conserved charges, which are extensive quantities like mass, angular momentum, and electric charge, besides the solution, also depend on the theory. So if we have a theory which admits, for example, metric G as its solution, we have two theories, for example, theory 1 and theory 2, which admit the same metric as their solution. The entropy, which is attributed to the same geometry in these two different theories, would be different because it also depends on the theory.
Shahin, may I ask something?
Please?
So the first statement that you made, that this Wald's derivation only comes from gravitational part of the action, that is true only if you have, I guess, a minimal coupling. For example, if it's a conformal scalar, it's not true.
Okay, so that's a very good point. Actually, if you just look at Wald's formula, it involves derivative of the Lagrangian with respect to Riemann curvature. Okay, and by my definition of gravitational part of the action was anything which has Riemann curvature in it. So it may or may not be that, I mean, we may not have we may have a non-minimal coupling, but not contributing to the entropy through Wald's formula, or we can have different kinds of non-minimal couplings which do contribute. You're right. So it depends on the form of the non-minimal coupling. Exactly.
Yeah, and then
what
I have
goes into.
Okay,
please.
Yeah, I just wanted to ask
Please
whether it is known that in general there is some this black hole thermodynamics has some generalization beyond Einstein gravity, in the sense, has it been proved that this is monotonic or non-decreasing, this entropy?
Okay, that's a very good question. Actually, Wald has a derivation for the first law, but if you're asking for the second law, I don't think that we have a so general formulation of the second law. I mean, that the entropy in any process which involves black holes increases. To my knowledge, we don't have a general proof of this, but we do have a general proof for the first law, but not for the second. But and actually, I'm not aware of any cases where the second law is not holding. So let me also add one other subtlety now that you asked. Actually, one may, once you go through the Wald's entropy formula and its derivation, there could be some very specific cases that the Wald entropy formula does not work. And that's because in that derivation, there are some ambiguities that one needs to, generically the ambiguities would not contribute to the entropy if we are computing it for Killing horizon, a bifurcated Killing horizon. So that's the condition that Wald's entropy formula should work for any Killing horizon, which is a bifurcated Killing horizon. But there are some very special cases, and we have explored that in our in a recent paper of ours, that some of these ambiguities do not cancel out in general. We have examples for black holes in Horndeski gravity theories. And we argue that we need to revise Wald's entropy for that. Okay.
But in general, if you have this non-minimal coupling of gravity to matter, then the entropy doesn't only depend on the metric, right?
Well, it depends on the full solution.
Depends on the full solution.
Metric is a part of that solution. Yes.
I see.
But the point is actually horizon angular velocity and temperature only depend on the metric, at least in the standard derivations. Basically, temperature is, for the case where we have a Killing horizon, is surface gravity. So regardless of what theory this solution is to, we have the same.
I see. So your point is that except for Einstein gravity, it's a very peculiar case. You have this universality of the entropy, which depends only on the metric. The entropy also is theory dependent, but the temperature and horizon angular velocity is only fixed by the metric universally.
Yes, yes, okay. Yes. All right.
So
basically, please.
No,
was there any question?
No, it was just somebody forgot to mute their mic, I think.
Okay, okay. So in first law of thermodynamics, actually, as we all know, there are two kinds of quantities appearing: the chemical potentials and the charges. The chemical potentials are those which are intensive and they do depend only on the solution. the other charges depend on the theory and the solution. This is, of course, the general picture. There could be some cases where we need to revise this picture. Also, I've made a very small remark here. I didn't want to get into this. And that is basically when we write laws of thermodynamics, depending on which ensemble we are working in, micromechanical, mechanical, or other things, there could be some slightly different corrections when we consider semi-classical corrections to this Waltz derivation, for example. But let me skip this point and we can discuss it later if there is time. Okay. So let me just summarize this part. First of all, a general property of any black hole solution is the horizon. And for the cases where we have a killing horizon, a bifurcated killing horizon, a Waltz formula is giving us the entropy as a conserved charge, which coincides with the area, Bekenstein-Hawking area law for the Einstein gravity. And the question which one can ask, and has been actually the main question in black hole thermodynamics or black hole dynamics question area, is whether this thermodynamic description is coming from an underlying statistical mechanical description, and whether we can basically with that, if we have that StatMech description, whether we can describe dynamical processes like black hole evaporation and hence eventually address the unitarity problem or the information puzzle. So, and basically the question we are going to ask is whether we can find a framework at semi-classical level to basically formulate black hole microstates. And this has been a very difficult question within the gravity theory, within GR in particular, because of the uniqueness theorems that we have. And basically uniqueness theorems are telling us that once you have a black hole solution, it's only specified by handful of parameters like their mass, angular momentum, and electric charge, and so on. And there is no room for large microstates which can lead to the entropy of the black hole. So basically, the main observation that we are going to explore in more detail is that horizon, this number D here, horizon may be viewed as the causal boundary, as we just discussed, of a large class of observers. And then we need to basically review, revise equivalence principle, which is the underlying principle for this diffeomorphism invariant theories in presence of boundaries. And basically the question we are asking is whether addition of a boundary, here I mean a horizon to the space-time, brings in any new features which can lead to black hole microstates. So that's basically the general idea. So let's basically try to see whether we can formulate this problem. So as we all know, equivalence principle tells us that all observers should give exactly the same description of local events in regions of space-time to which they have causal access. So, basically we know that any observer is equivalent to a coordinate system and vice versa. That's basically how we formulate equivalence principle. And this means that the theories which are respecting equivalence principle are diffeomorphism invariant theories. Okay, so let's consider two metrics which are related by diffeomorphisms. X going to x plus xi mu, under which the metric transforms in this way. And basically any two observers whose metric are related in this way or in two different coordinate systems like
Shahin?
this, please.
Yeah, so I'm a bit confused about your statement. So in JT gravity, we know that, for example, diffeomorphism is broken to SL2R, but the equivalence principle is still there, no? At least classically.
Well, in the JT gravity, I think the action is still diffeomorphism invariant. If you choose
the boundary,
specific background, if you choose a specific background, then you're right. But the theory, not the solution, the theory is diffeomorphism invariant.
Yes, but essentially the boundary condition is responsible for breaking it to SL2R only. Yeah, you're right. I mean, it's because it's the way you have to choose the boundary is sort of dynamically chosen in a way, because it's a place where phi is constant, and so you're saying that it is sort of a spontaneous breaking, not really like a
yes, exactly.
I see. But you are saying something more drastic. You're saying it is not, you want to advocate some kind of not spontaneous breaking, but an explicit breaking of diffeomorphism invariance.
Okay, so let's go through this. It's not actually a breaking. It's more like in gauge theories, we usually do gauge fixing. Let me come to this.
Okay.
So as I just mentioned now, the fact that we have some degrees of freedom appearing in the action, and they're defined up to some gauge transformations, local transformations like these diffeomorphisms. This is a generic property of any gauge theory, and physical observables are those which are gauge invariant in these theories. So basically, generically, when we have a gauge theory or diffeomorphism invariant theory, there is a redundancy of the description which should be removed by gauge fixing. And so that's the standard practice. There's also this other notion of spontaneous symmetry breaking, which happens at the level of solutions. When you basically extend the theory around a given solution, you may basically break a part of that symmetry. That's not what I'm talking about here. Okay, so but let's basically try to study this gauge fixing process more closely. The question I'm going to ask is whether once you fix a gauge, whether there are some remaining residual gauge transformations. So that's basically the question I'm going to ask. But now I want to ask this question in presence of boundaries. So when you have a boundary at your space-time, in order to define your theory, your field theory, in general, when you have a boundary, you need to specify boundary conditions. And these boundary conditions may not be respecting your gauge fixing, or basically a part of your diffeomorphism invariance or gauge symmetry could be broken by this specific choice of the boundary conditions. So, but generically, since the theory is a local theory, the symmetry is local, and these gauge symmetries are local, any choice at the boundary for any given boundary condition does not actually break the gauge symmetry or diffeomorphism anywhere in the bulk. But it could be good enough to make a measure zero subset of diffeomorphisms or gauge transformations physical or non-trivial. Okay. So that's basically the idea that I'm going to formulate, and as we'll see, the answer is positive. But let's go back to the theory, the Einstein gravity, for example. In presence of boundaries, Einstein field equations are generically well-posed, second-order differential equations. And this means that the metric, which is the solution to this field equations, is completely specified, giving the values of the metric and its time derivative on a Cauchy surface. And basically, the data that the initial data that you put in your Cauchy surface basically is conserved by your dynamical evolution as set by, for example, Einstein equations. This is basically the well-posedness problem, right? So the information about the Cauchy data could be recovered at each and every constant time slice, for example. So this is the Cauchy data is a conserved quantity. And a part of this Cauchy data could be not compatible with the full diffeomorphism symmetry. That's the whole point. Okay. Let me just do some counting for the bookkeeping. Let's take a d-dimensional spacetime. For the time being, I'm going to only consider a pure gravity theory, pure Einstein gravity theory. We can generalize the discussion in a trivial way almost. So let's just consider pure gravity in d dimensions. The metric has d times d plus 1 over 2 number of components, which are generic functions of d variables in the d-dimensional spacetime. We have d times d minus 3 over 2 propagating gravitons and d number of diffeomorphisms, which allows us to fix d number of components of the metric. Then we have d times d plus 1 over 2 field equations, out of which the same number, d times d minus 3 over 2, are second order differential equations. They are the so-called dynamical equations. And then we have d number of constraints, which are basically first order equations. These are coming from the Bianchi identity. So basically in the upper part, I've given the degrees of freedom decomposition, and in the lower part, we have the decomposition of the equations of motion. So there are d number of functions on a codimension 1 surface sigma, a d minus 1 dimensional space-like or partially null surface, which need to specify my initial data on this surface and then let the equations evolve in time. As I just discussed, the information about on this initial data by definition is conserved as we move away from the Cauchy surface. Okay, now basically I'm going to discuss that this Cauchy data, the data that I'm basically fixing on a given codimension 1 surface sigma, it could be labeled by what I just called non-trivial diffeomorphisms and the charges associated with these non-trivial diffeomorphisms. So I'm basically, this is an equivalent way of parametrizing or describing the solution space. Okay, so to see how it happens, let's just take, for example, sigma to be a null surface sitting at r equal to 0. And I can write the most general form of the metric in this form, metric 1. These functions f, mu, gi, and hij are all functions of v and x and r. And in order r equal to 0 be a null surface, I need to impose this condition among them. So
Shahin, you're frozen.
I think we lost him. Is he
Yeah,
there? We lost him.
he's. Yeah, it happened once earlier too. I guess he will be back. Yeah, okay, let's wait for Shahin to come back.
His connection is always flaky, if you noticed. Even when he asks questions, it used to go away.
Yeah, I mean, it was not his connection, actually. It was mostly his speaker thing. But now it is fine. But the connection is okay. I mean, except that sometimes he's being logged out by the system or something. I don't know what's going on. So he has gone behind the horizon now.
Maybe you should pause the recording till he comes back.
Yes, we can do that. Recording.
Sorry.
Yeah. So, but you can share again, and yes.
Okay. Okay. Good. Okay. So. Okay, so sorry for the interruption. Let's go back to this metric. This is the most general form of the metric we can write down with the condition that r equals to 0 is a null surface. And in this metric, there are two scalar functions, one vector and a tensor, as we just saw. Actually, the tensor part could be, we can take it trace out of this, and basically then we have three scalars, a vector, and one traceless symmetric tensor. So these are basically the vector, tensor, and scalar with respect to codimension 2 surface sigma v, which is basically constant time v slices on sigma. And so this is just a parameterization of the metric, but we need to still impose equations of motion. And if we impose the equations of motion, Einstein equations here, the symmetric traceless part of the degrees of freedom dh will be described completely through two functions on a codimension 1 surface, v and xi, basically h0 and h prime 0. And the same is also true for the vector part, which is basically described completely by a codimension function, a vector function on a codimension 1 surface, basically on the null surface at r equal to 0. And then equations of motion are basically telling us that out of these three scalars, two of them are independent. So and we take these two scalar functions to be f0, which is again a function on sigma, and h0, which is again a function on sigma. So in general, my solution space, this is the most general solution which one can write down around r equal to 0 null surface, is described by two scalars, a vector and a tensor, around this null surface. So basically, this is what I'm going to call this family of metrics. I'm going to call solution space. And the only things that besides the equations of motion that I have used is that I've assumed smoothness and Taylor expandability around this r equal to 0 surface. I have not imposed any particular fall-off behavior around r equal to 0. So I've allowed any general thing, any general behavior for the metric. But I've imposed the equation of motion perturbatively around r equal to 0. Let me again emphasize that r equal to 0, while a null surface is not a special place in the space-time. It could be any null surface in your space-time. It could also be the horizon, for example. Once again, the solution space is described by tensor modes corresponding to gravitons, two scalars, and one vector mode, which is basically d minus 2 number of functions over sigma. And this is basically the maximal solution space that one can have. Any solution in GR, in a pure gravity theory, could be written in this form, at least close to a null surface. Okay, so let's now ask, we have a null metric with the r equal to 0 as the null surface, sigma. We want to see whether we have which of the diffeomorphisms are basically keeping us within this setting. In particular, which diffeomorphisms are keeping the sigma equal to 0 and null surface. In equation 2, actually, I've written the form of these diffeomorphisms, which keep r equal to 0 as a null surface. We can basically shift v by any function of v and x. I've called it t. We can rescale r by any function of v and x, which I've parameterized through this function w here. And xi could be basically defined up to any diffeomorphism, which is a function of v and xi. These are basically expansions around r equal to 0. There could be higher orders of r. And one can very explicitly and very easily see that these diffeomorphisms keep the form of the metric invariant. However, it shifts some of these functions that we had in the metric in a particular way. And this means that basically these diffeomorphisms move us within our solution space. Okay. These functions are going to generate for me what I'll call residual diffeomorphisms, because these are residual because they keep this sigma, the r equal to 0 and null surface. As I just mentioned, these diffeomorphisms, by definition, keep us within this solution space because they are just diffeomorphisms. Einstein field equations are the only things that I've used, and they are diffeomorphism invariant. So these diffeomorphisms move us within this solution space. This means that basically they transform functions f0, mu, h0, and so on, which we have in the metric. These deltas are linear in my symmetry generators and also depend on the background functions f0, h0, and so on. So if we just do the counting again, we have, besides the propagating gravitons, which are parameterized by this capital Hij, there are 2 plus d minus 2 number of functions over sigma in the solution space, and we have exactly the same number of functions over sigma in our residual diffeomorphisms. Just to remind you, we have t and w, which are scalars, and yi, which is a vector. So the number of this non-propagating degrees of freedom in our solution space is exactly the same as the residual diffeomorphisms that we remain with. And basically, as I just mentioned again, residual diffeomorphisms can rotate us within the solution space, and hence they are symmetry generators. So let me just remind you of what a symmetry was in the standard classical mechanics. A symmetry is basically something which moves you from one solution of the same system to another solution of the same system. And then there are 2 classes of states in our solutions or fields in our solution space: the hard modes related to propagating tensor modes, and the soft modes related to this d number of other functions, 2 scalars and 1 vector mode. And basically, these soft modes are boundary modes, which I mean by a boundary mode, I mean something which is a function over v and xi. Over sigma is a generic function. You can view this as fields over sigma. And so basically, in my solution space, besides my gravitons, which are propagating in the bulk, I have boundary modes, which are only propagating at the boundary on sigma. These boundary modes are never propagating in the bulk. However, they interact with the bulk modes, which the gravitons which are passing through this sigma, they interact with its boundary modes. The boundary modes can also interact with themselves. Now what I'm going to describe is how one can label and basically parameterize these boundary modes. Before that, I basically first argue that this solution space is actually a phase space. Hence, we have a solution phase space. There are many different ways to argue for the fact that solution space is a phase space. One convenient method is covariant phase space method, which means that my solution space is equipped with a well-defined symplectic structure through which I can define Poisson brackets. Okay, using this covariant phase space method, I can associate conserved charges or charges given by surface integrals to these symmetry generators, the non-trivial diffeomorphisms. And these charges could be used if they are well-defined and finite and so on. They could be used to label my solutions space, at least the soft part of the solution space. Okay, so you may ask, what are these surface charges? They are given by integrals over constant V surfaces on sigma. They are linear in generators T, W, and Y, and the integrand is, besides this V, W, and Y, which is linear in it, involves functions which are defined on my solution space. So here labeled by F0, H0, and GI0. Okay, so let me very briefly go through this solution phase space or covariant phase space formalism and basically tell you how one can define a well-defined symplectic form and Poisson bracket.
Shahin, can I ask something here?
Please.
This is a bit confusing because normally if you say that these kind of solutions, these are inequivalent solutions, if you have sort of some kind of asymptotic boundary. However, here you don't have a boundary, you just take any null surface. So is it correct to say that only if you view the null surface as sort of a boundary, then only you could make this statement that these different soft modes generate new solutions, inequivalent solutions?
Okay, so first of all, this null surface could be anywhere in the space-time. And even in the beginning, I basically discussed that I need not take a null surface. It could be a Cauchy surface. It could be any constant time slice if you want to make the problem easier. You take any constant time slice. You can put any field configuration and the derivative of the metric on this constant time slice as your initial data, and then let this system evolve, right? So you could have asked, how can I parameterize my initial data? Usually we say, okay, it's basically a part of the metric on the constant time slice or the momentum of the metric on the constant time slice. But equivalently, you could have used the same formalism that I'm just talking about. There are always some residual diffeomorphisms. For example, in that example, we have a foliation preserving diffeomorphisms on the Cauchy surface, which by the appropriate choice of the coordinates on the surface, I can make the initial metric on this surface to be, for example, delta ij, right? I can always do this. But if I insist that I want the metric on my initial slicing be such that the metric is Gij as a function of x and x on this Cauchy surface, there is a non-trivial information there, right? And I'm just trying. I'm not saying anything.
Yeah, I understand. I understand what you're saying, but I think essentially you should have something in mind. There's some asymptotic conditions in mind, in implicitly, if not explicitly, because I think what the kind of generators that the kind of different solutions you're talking of, they are related to this as if you have an asymptotic symmetry group, then each will have the conserved charges. They will reduce to that in that limit. But then if you, suppose if you have all these inequivalent solutions, how do you really know that they're inequivalent? In what sense they are because first of all to define them as solutions,
because I can associate some labels which in general they could be viewed as conserved charges, right?
Yeah, I understand what you're saying, but normally we say that you have some sort of a notion of solution space. I think there's some kind of, I don't know. I mean, if you have an asymptotic symmetry algebra, you could talk about like normal fall-off conditions and make this distinction, right, between these inequivalent solutions. But here it looks a little bit. Okay, you're putting my hand, which probably is the right thing to do. But I'm just saying, so you're somehow extending the notion of this inequivalent solutions to a very general setup, but it's not quite clear that it is a very well-defined thing to do. It's just maybe a technical issue.
No. Actually, I would say for the same reasons that in the asymptotic behavior of the solutions, you may again, that's your choice. That, for example, you say, as if the metrics in the asymptotic region are different up to some order of 1 over r, then I declare them as being distinguishable, right? This is your choice.
Okay, sorry.
Even then, in order to specify the theory, besides the action, you need to also specify what you have as your initial data, as your boundary action, both, right? Okay, and thanks. All what I'm saying, action and boundary degrees of freedom. Okay.
Okay.
So, let me just run. Suppose that we have a general field configuration. I denote them by phi bar, the on-shell field configurations, and some perturbations which are on-shell, meaning that they satisfy linearized field equations. And this phi boys and the one form, there are two general families of this delta phi's which we are usually interested in. Delta phi could be generated by some diffeomorphisms, as we discussed the examples that I just discussed, or they could be parametric variations. For example, in the Schwarzschild solution, you can consider the difference between two solutions with mass m and mass m plus delta m. So this metric, which is satisfying the linearized equation. Okay, so then I can define the symplectic structure through an integral of this symplectic potential W over a sigma, Cauchy surface sigma. And this W is finite, closed, and non-degenerate two-form over the solution space, and a d-1 form over the space-time. So you can see for more details this classic references. But I'll tell you now how you can define, you can obtain this W given a theory. So this W is delta of some function, which is a d minus one dimension, d minus one form over space-time and a one form over the solution space. And this theta is related to the Lagrangian top form in this way. So the variation of the Lagrangian on shell is a total derivative, as we all know. And this theta is defined this way. So this is one simple basic way to define theta and hence W. And then out of that, you can define this symplectic form omega. This has the required properties of symplectic form, namely that is conserved and is non-degenerate. I'll just skip through the discussions. But since this W on shell is, d of W is 0 on shell, it could be written as d of something, d of k. We can compute this W over one of these symmetry generators and hence define this k with index chi, which is basically associated with the symmetry generator chi. And one can through this k by integration over codimension 2 surface, we can define this charge variation delta slash q. And if the charge is integrable, we can basically define q of chi itself. So if it's integrable, if we have this property, or in terms of W, if we have this. And if it is integrable, we can define this charge through this surface integral and an integral over a generic path in the phase space. Okay. And now the rule of the game is that if for a symmetry transformation chi, we can define a non-zero, well-defined finite q of chi as a function over the solution space, then this chi is a non-trivial physical transformation, or is a non-pure gauge, if you wish. And this q of chi is labeling my physical degrees of freedom, but on the boundary. One can define these q's are functions over the phase space, because these are functions over of phi. You can define the with the symplectic form, you can define Poisson brackets of these charges, which are basically one can prove that they satisfy in general an algebra of this form. And I'm going to use this q's to label my soft modes, the boundary degrees of freedom. Let's basically go through the example of three-dimensional gravity on a null surface and see how it works. So this is my 3D action. I allow for any cosmological constant. This is the equations of motion. All the solutions are, so this is the general the theory that I can write, and then I have in mind, and then the solution space is basically parameterized in this way. I'm just repeating what I had for general dimensions here for three-dimensional case. R equal to 0 is a null surface, meaning that I have this three functions labeling my solutions space, and this F1 and H1 by using equations of motion. So once again, capital F0, little f0, omega, and eta are the three functions that are v and phi, which are labeling my solution condition. So I have a solution space which has 3 independent functions in it. The symmetry generators are of this form, essentially of this general form that I just showed before. There are t, w, and y functions there. The symmetry algebra, which is basically the Lie bracket of the among these vectors with these components t, w, and y, is satisfying this algebra. So this is basically my symmetry generators and their algebra. And this algebra, if you just look at it carefully, what you see is this is what I call null boundary symmetry algebra, is the diffeomorphisms on a 2-cylinder and a while scaling. So the diffeomorphism on the cylinder, the cylinder is parameterized by v and phi. So this t and y directions are generating the 2-dimensional diffeomorphisms on the cylinder, and this w is actually generating scaling on the r direction, because this CR is something proportional to the R at the leading term. So this is the algebra that we have here in equation 10 with this T12, W12, and Y12 is basically diffs on cylinder, a null cylinder, plus a wide symmetry. This argument was so general, as we just discussed, in any dimension. And in any dimension, this I would expect that the symmetry algebra is now replaced with diff of cylinder d-1, the null cylinder d-1 dimensional null cylinder, plus the while scaling along this null surface. Okay, going back to this solution space, as I just mentioned, there are 3 functions of v and phi, which I can take 3 combinations of this, which appear in the charges, and label my solution space through these 3 functions, not the original f0s and omega. So the explicit form of this in terms of the functions which appear in the metric is given in the paper, and you can see it. I don't think that is illuminating to show it, but there are 3 independent functions. Basically, that's the takeaway from here. One can compute the charges and their algebra just going through the standard computations. That's what we get for the charge variation using the same solution phase space method that I just mentioned. This charge is not integrable because of this last part. The charges associated with W and Y are integrable, but the one associated with T is not integrable. So the general name that people have given to this is that the Y, which, if you remember, is a transformation, general coordinate transformation along the phi direction, is basically generating super rotations. The T, which is associated with the translation along the V direction, is called super translations, and the W is basically the wide scaling. One can now one can ask whether this charge, which is not integrable, could be made into an integrable charge, and the answer is yes. If we make a field-dependent change of basis, namely, if instead of T, Y, and W, I take my symmetry generators to be given by T hat, Y hat, and W hat, defined in this way, I can rewrite the same charge variation, exactly the same expression, but now in terms of these hatted generators, and we find that actually the charge becomes integrable in this new basis or slicing of the solution phase space. Okay, so to summarize, I have now 3 symmetry generators, W hat, Y hat, and T hat, and 3 charges omega, epsilon, and p. And this is basically the basis where the charge is integrable. One can work out the algebra of these charges, basically you going through the standard Poisson bracket. And if you want, you can do this quantization, the standard quantization scheme, replace the bracket with the commutator, and promote this as operators acting on the solution space rather than functions on the phase space. And this is the algebra that I get. The omega and p are actually satisfying a Heisenberg algebra. The epsilon is giving me a weak algebra, and omega and p are functions of weight 0 and 1 and 0 in this weak algebra. So and in particular, note that the role of h bar is now played by 1 over hg. Okay. Can I take 5 more minutes? I think I've run over time.
Oh, no, sure. You can take 5 more minutes without problem.
Okay. Sorry. One can ask whether the basis which makes the charges integrable is unique. I already showed one such slicing of the phase space in which the charges are integrable. And the answer is there are infinitely many such bases actually, which the charges are made integrable. And in particular, I can use this change of basis or slicing on the phase space to make the algebra look even more nicer. And here is one more change of basis. Instead of hatted objects, I'm going to objects with tilde, w tilde, t tilde, and y tilde. And instead of epsilon, I introduce this s. And essentially, physically, what has happened is that out of the super rotations epsilon, I've taken out the orbital part, and this s could be viewed as some internal super rotation part. If I rewrite the algebra of these new objects, new charges, s, p, and omega, that's what I find. Then now the algebra becomes a direct sum of a Heisenberg algebra, the first line, and this one, which is the diff of S1. This S now commutes with P and omega. And this is basically diff of S1. Okay, so let me try to summarize and conclude and see how it may help with the black hole microstate problem I mentioned in the beginning. We just discussed that in presence of boundaries, we need to also consider new boundary degrees of freedom. This is actually something which is very familiar in, for example, electromagnetic theory. If you want to formulate your electromagnetic theory in a box, we usually assign some new degrees of freedom to the box, some boundary currents and so on is basically added to the boundary to make sure that we have a well-defined description of electromagnetic fields inside the box. So the presence of this boundary degrees of freedom is very familiar. Now the only thing which is added to this game here is that this boundary need not be a real boundary of space in your space-time, like the example that I just mentioned. It need not be a specific physical box that you have in your space-time. It could be just, you may consider some region in your space-time and declare that I want to define my theory within this box, within this region. And now, in order to have a well-defined formulation, typically what I need to do is to add some assign some new degrees of freedom, the boundary degrees of freedom on the boundary of the region that I'm going to describe the field theory inside. Why is it meaningful to do the same, to basically play the same game with the black holes? Because Horizon is, as I just discussed, is a boundary of a big class of physical observers. So physical observers who are outside the horizon and never cross to the horizon view the horizon as their boundary. If I'm an outside observer, I should be able to have a well-defined description of physics outside the horizon. Remember that the two sides of the horizon are causally disconnected. So this would only be possible if I add the required boundary degrees of freedom at the horizon. Let me emphasize that I'm not adding any physical object at the horizon. The horizon is just a null surface, but the observer who is living outside as if assigns some new boundary degrees of freedom. And these boundary degrees of freedom could be labeled by the charges that I just mentioned. I have a very well-defined formulation which can be used to label all these charges. Again, there are some technical comments that, for example, this is sigma need not be a null surface. It could be like a stretched horizon. It could be a time-like surface. But basically, all these discussions would go through for this case as well. And okay, so this is basically at the kinematical level. Now for the set of observers outside the horizon, what I have is usual gravitons which are propagating the bulk, plus these boundary degrees of freedom which are residing at the boundary. And the only thing that I've used to label, identify this boundary degrees of freedom is the diffeomorphism invariance, actually, nothing else. The same diffeomorphism invariance could be used to basically give me the dynamics interactions of these boundary degrees of freedom with themselves and with the gravitons in the bulk. So which was basically a more precise form, which is a more precise description of the soft hair proposal by Hawking, Perry, Strominger. They just as I understand their proposal, it's not substantiated. We are now trying to basically give a general formulation of that idea. And we basically discussed that how one can label this to-do list, and we need to basically go through this more carefully. And we need to carry out the quantization procedure over this phase space. And actually, the first step is to see whether this, even at this kinematical level, we are able to reproduce the black hole entropy. So that's the first test. And in order to do that, actually, we need to, these algebras that I just mentioned are infinite dimensional and entropy is finite. So we need to basically truncate the representations of these algebras in some way. And maybe that's some new addition which comes through the quantization procedure. That's something to be seen yet. We have a proposal actually for three-dimensional examples, what we call fluff ball proposal, which provides this basically this quantization. But that proposal, the fluff ball proposal, is specific to three-dimensional cases. It may be possible to generalize it to higher dimensions. That's something to be seen. And then the procedure of defining charges and basically changing slices and bases on the phase space and so on is sort of still needs to be understood better. There are some technical remarks here. I'll basically let you read through them. And this is my last slide, and maybe I can stop here, and I'll be happy to take questions. Thank you.
Thank you, Shahin, for this beautiful talk.
Sorry, I went over time. And for
No,
the
it was perfect. It is the usual time, like 1 hour 15 minutes anyway. So let's take questions from the audience now. Okay, maybe I can start with one question then. So
Please.
my question is that like Wald had a general formula for these charges, depending on an arbitrary Riemann. You're assuming it's dependent on Riemann curvature. It's a local action. So could you also have some? I mean, okay, maybe the integrability would be hard, but some, at least some formulation that could be very general to the theory, whatever theory of gravity, or such.
Okay, so the entropy. Okay, so that's actually Wald's entropy formula is an extension of usual Noether's theorem.
No, I'm not talking of the entropy. I was talking of
the entropy, not the entropy variation. Sorry, I didn't. So would you repeat the question then?
Well, you had this charges, this conserved charges. Could you write them in any theory? So what I was wondering is that that you had these two different deformations. It could be that only one of these things could be generalized to higher derivative gravity, and the other one cannot be that easily. Or I was just thinking.
No, actually, that's so. Let me just review what was the steps that the first step was to build the solution phase space, right? Here, actually, the metric is very general, but the very fact that, for example, we can do this, these expansions are general again, but the very fact that these other first order functions in R are all determined in terms of this lower order functions is coming from equations of motion, right? So equations of motion are crucially used here. If you have a higher derivative theory, the equations of motion would be different, then the solution space would be different, right? So I'll have a different solution space. The expression for the charges would also be different in a general theory. So the expression for the charges that I wrote here was computed for the Einstein lambda theory. But if you, for example, take new massive gravity or one of the zillions of three-dimensional gravity theories that people have written, the expression for that's true, but our general statement is theory you take, there's always a slicing in your phase space, which makes your charges integrable if there is no propagating graviton in your system. So we need to prove this statement, but we have a very clear statement on this. We are working on the general proof and some different examples which shows this is happening.
Yeah, my question was this, whether you could write these objects W, Y in terms of the Riemann curvature in arbitrary...
these are part of the diffeomorphisms. So W, Y, and T are symmetry generators. This omega, epsilon, and A are the charges.
Are the charges. Sorry, yes. Yes. Sorry, yes.
Okay. Okay, so yes and no. Yes, in the sense that these are made out of this metric, the functions that I have in the metric. The curvature is also written in terms of the functions that I have in the metric. So they are made out of the same functions. But if you're asking the curvature of the space-time or extrinsic curvature of this surface, they are different, right? Yeah. I don't think that all this information is there in
I
the
see.
curvature of the space-time
I
necessarily.
see.
But if I add to that the extrinsic curvature of the surface, I think they would include it.
I see. Thanks for this comment. And,
Sorry, I didn't get the question.
No. I think I got the answer. I mean, it was not a very well formulated question anyway. But you could have some kind of a definition of this integrability in an arbitrary theory. If you
Yes.
consider some sort of higher derivative corrections also, that's what you're trying to say.
In principle, yes. I gave you our sharp conjecture or proposal that regardless of the theory, when there is no propagating graviton in the system, the charges could be made integrable in appropriate basis. But one needs to prove this. And this was true for regardless of what the theory is.
Then my second question is, could you, because you said that you could apply it to any kind of null surface, could you also apply it to some kind of extremal surface, like for example, some sort of a quantum extremal surface or any kind of one of these extremal surfaces that come up?
Yes, in principle, that's possible. And actually, with one of my collaborators, we were actually discussing exactly the same thing. And we are trying to see whether the information in the RT surfaces could be encoded in this way.
So you're saying, but then what is the interpretation of these charges for an extremal surface?
That's a good question. And so I'm just, this is my guess, and this is a work in progress. So Bartek, Sheikh, and collaborators have this idea that we have this modular Berry connection, which is basically, we have modular Hamiltonian, and you can also, on similar footing, you can define modular Berry connection. And our proposal is that, or our idea is that the information in the modular Berry connection is encoded in these charges. So if I don't know if it was clear enough, but so that's a very good question. We are trying to study some aspects of it.
Okay, yeah, that's interesting. We look forward to that. Okay, Shahin, then it was very nice to have you here, and hope to have you again, maybe where you can talk about your new results. And
thank you.
So have a nice rest of the day, and goodbye to all, and see you again next week, and see you again.
Okay. Thank you. Okay, thank you very much for having me here and for basically the questions. Please let me know if you have any comments or further questions through email. I'll be happy to discuss it further. Thank you very much.
Thank you, Shahin, again. Bye.
Bye.